Hello everyone, I hope you guys are doing good. So today is the third lesson of this electrostatic, and today again I'm going to do the Coulomb's numericals on the Coulomb's law. Well, I believe that whatever we started, we should finish that properly, like in a lot of cases I just find that students do the basic questions and they get the feeling that okay, they've understood the topic properly and they just leave that and they move on to the next topic. Well, that's a bad idea. What happens, like in the standard test, in the standard exams and all, the questions will be of slightly better level, So what a lot of people do, a lot of students do, they just leave till certain level and they assume that the chapter is done. Okay, well, we're not going to do that over here. We're going to try and finish every possible thing, all type of questions that could be asked from a particular topic. Okay, all right then. In the last video I've given one homework question which I'm going to discuss at the end of today's video. Today let me see one of the variations of when we have the time period need to be found. Like if you remember in the last video I've just told you like to find the time period of the body of a charge displaced along the x-axis. So in the continuation to the same question, let's see, I have an example for you. Let's say probably example 1 for the today's lesson. I'm having charges placed like this, plus q and plus q at a distance, let's say probably anything, let's keep it 2L. Alright, now I'm going to place a charge at a perpendicular bisector of these two line segments. Let's say I have a charge over here on this bisector, a charge q over here, let's say negative q over here. Now my question to you guys, listen to me carefully. Find the time period if this charge is slightly displaced along this axis, right? Let the mass of the charge be m. My question is, what's going to be the time period? I'm sure you guys have understood so far that if I displace this body, it's going to execute an SHM, right? So my question is, what's going to be the time period if this body is displaced slightly? I'm emphasizing the word slightly. If it is not slight, it's not going to be an SHM. Well, okay, along this axis. Fair enough. Again, the pattern, the standard way of doing it, they remain same. I'm going to find the force on this, and that we should do the comparison with F equals negative of kx, and then we're going to use T is equals to 2 pi m over k. Fair enough. Okay, let me just displace it over here slightly, probably over here by a distance of, let's say, x over here, small x. So as of now, let's say the value is x. Let's say what is the force on this? So the forces on this would be in these two directions, along this negative and positive, and somewhat like this in this direction, right? Let us take the component. Since the values of charge is same over here, let's say it's going to make some angle theta, even this is going to be theta, and horizontal component will get nullified on both the sides, right, because of the symmetry. The forces would be acting along this, the two forces, that's going to be, let's suppose this force is F, even this is going to be F. Then in this side I'll be having some component of that should be 2F cos theta. Okay, so if it is coming down, so let's say it's going to be minus of 2F cos theta, since I'm just pointing it towards downward, the force is down the axis. So can I just say, guys, F equals negative of 2F cos theta. What I need to do now is to find the value of F over here. Okay, let's say this distance is x. Let me write it here. And this is probably L, 2L. So this is going to be, let's say, L. So the value of F should be how much? F net. This is F net. So negative 2 times of F will be how much? K Q Q over this distance should be how much? L square plus x square. L square plus x square whole square. So root will get over. Cos of theta. Well, cos theta should be how much? X over this distance R, let's say. That's going to be x over L square plus x square to the power of 1 by 2. So this is going to be negative of 2 times of kq x over L square plus x square to the power of 3 by 2. Okay, now we assume that L is quite greater than x. Then I'm going to ignore the value of x in comparison with L. I'll be left with negative of 2 times of k q over L q times of x, And if I do the comparison with f equals to, this is f equals to negative kx, I'm going to get k equals 2kq, and of course I just missed out this small q over here, so let me put that small q. Okay, 2kq over lq. So the time period should be how much? 2 pi root over m over k. So I'm going to write ml cube over 2k q and q. Fair enough? So yeah, I've discussed both the possibilities along horizontal as well as along the vertical. I'm sure you guys have learned this one, right? Fair enough. Let's go to the next question. Alright then, let's have an example based on the pendulum question. Example 2. Okay, let's say for instance, my question is, in a system like this, I have a charge q and mass m. I have one more charge of same magnitude q and mass m. It is found that the equilibrium exists at 45 degree. So let's say the equilibrium exists at 45 degree. Okay, so the first part of the question, equilibrium exists at 45 degree. Fair enough? It's possible, yeah, at certain angle the body is going to be, the mass is going to be in equilibrium with these charges. Now my question is, if I release it at an angle of, let's say, 53 degree, alright, if I just pull it up over here at an angle of 53 degree and then I release it, so definitely the body will try to come down, isn't it? Because the equilibrium exists at 45 degree. So if I release from 53, it will definitely try and come down to the equilibrium position. Now my question is, find the acceleration at the point when the bodies are released from 53 degrees in terms of g and all. Okay, so the question is, find acceleration at the moment when it's released from, let's say, 53 degree. Fair enough? Okay, so as you can see, this question is in two parts. One, the equilibrium conditions, and the next is finding the acceleration when it is released at certain angle. So let's see how we're going to do it. First of all, let me find out some information from this, because my question is, find A in terms of m, in terms of g, I would say, in terms of g. Okay, so at the when the case is equilibrium, let's say the force is acting on this object. This is going to be mg downward. There should be an Fe electrostatic force. Away from it, let the length of the string be L. Okay, let me join these two. There's going to be a tension in this string T, and they're going to be, let's say this is 45 degree. So T cos 45 acting upward, and here we're going to have, let's say, T sine 45 along this. In the equilibrium position, net vertical should be 0 and the net horizontal should also be 0. I'm going to use that thing over here. So can I just say, guys, T cos 45 vertical component should be equals to mg. From here, can I say T should be equals to root 2 times of mg, because cos 45 is 1 over root 2. Fair enough. Let's have equation 1. Let's look for the horizontal equilibrium. Then Fe should be equals to T sine 45, which is going to be T by root 2. And what's going to be the value of Fe? We're going to calculate that. That should be K Q square over the distance between them. Well, if it is L, this part should be how much? L sine theta. So this part should be L sine theta. So this entire length should be 2L sine theta. And theta over here is how much? 45. It should be L over root 2. So this entire length should be how much? 2 times of L over root 2, which means root 2 times of L. Well, that should be root 2 times of L whole square should be equals to, what is the value of T? T is nothing but root 2 times of mg, root 2 times of mg over root 2. This will have cancellations over here. So what I'm going to get over here is kq square over twice of L square equals mg. It means kq square over L square should be 2 times of mg. This is what I've got from the given information. Now let us look at the second part of the question, when it is released at 45 degree. Fair enough? Okay, so let me just draw the diagram over here for releasing part of the question. Let's say the bodies are released in such a way that the angle between them at the instant of releasing is 53 degree. So let's say this is 53 degree, and of course this is 53 degree. Okay, the moment I release this, the body would try to come down to the mean position. Well, when we talk about the acceleration, we know two kinds of acceleration, radial and tangential. Since the body is not moving along the radius, over here we'll have only tangential acceleration. So our entire focus should be on the tangential acceleration. So let me draw a tangent. So anything which is going to happen over here should be along this direction, and that's a tangent. Alright, let us see the forces acting on this. The first force which we need to have is your mg acting downward. Alright, now F electrostatic should be this way. Now let us try and figure out the angles between them. Okay, so let me pull it over here, this thing. Okay, this is okay. Here we have tension in this string, in this case. Now since the acceleration is happening along this tangent, I need to find how much force we have as a driving force which is acting this way, and how much force we have acting along opposite of it. If I could figure it out, I will be done, right? So that's a concept, and that's the idea behind solving this kind of question. So if this is 53, let me just have a little bit of geometry coming over here. If it's 53, this should be 90 minus 53. Well, that's okay, that should be 37. It should be 37 degree. Guys, if I look over here, well, 37, 53, 37, 53 degree, this one, 53, 37, 53, this should be how much? 53. I hope this part is clear to all of you, how to find the angle. That's pretty much hot in Bangalore now. Okay, sweating. So these angles, I actually found it out. Now let's see the forces. A component of mg would be acting along this direction, mg cos theta. A component of force, and theta over here is how much? Let's say right away 53 degree. And there would be F electrostatic in this direction, Fe cos, okay, this is mg sine, this is mg sine 53 degree, and this is going to be Fe cos 53 degree. The acceleration is along this way, so can I just write A equals mg sine 53 degree minus Fe cos of 53 degree over m. Fair enough, all of you? Now let us put the values. So before we know that, those for people, sine 53 degree is 4 by 5. Length of the string is, let's say, L itself. To find the value of Fe, I must be knowing this length, of course, that should be L sine 53. It means 4L over 5 should be this part, right? So the entire length should be how much? 8L over 5. Okay guys, so I'm going to have mg sine 53 degrees and nothing but 4 over 5 negative Fe, well, that should be kq square over 4L by 5 plus 4L over 5, 8L over 5 whole square. Cos 53 is 3 over 5 divided by how much? M. Okay, let's keep going. Now I'm going to have some sort of help from here. So I'll be having 4 mg over 5 negative if I just do some sort of calculations over here, I'll be having 25 up 5, so it's going to be 5 times 3, 15. 15 over 8 kq square over L square, right? 1 over m. Okay, let me write it here. So that should be kq square over L square. Guys, I know that's going to be equals to 2 times of mg. So I'm going to take out mg common, 1 over m. I'm going to have, let's say, m common. I'm going to have 4 over 5 g negative. This entire thing is 2 mg. So I'll be having 15 over 4 g. I hope you guys agree with this, right? kq square over L square, 2 mg. So 2 times 15 by 8 is going to be 15 by 4. G is here, m has been taken out, cancelled. So that should be, if I look at the LCM, well, that should be how much? 20. I'll be having everything is all right. Okay. Oh, well, there's a mistake. We had to write 64 over here. 64, 8 square is 64. So it means this should be 32. Okay. Now 20, well, the LCM will be how much? 10, 160. I'll be having 8, 128 negative 75 times of g. Well, that should be how much? I hope it's correct. Yeah, it's going to be 3. It's going to be 5 over 160 g. That should be the value of acceleration. Make sure you do check up the calculations part. Yeah, I think 32, 8, 128. Yeah, fair enough. 575. I think it's correct. Yeah. So the value of acceleration in this case when it is released at 53 degrees should be how much? 53 over 160 z. Guys, quickly note it down. Then we're going to have one more illustrations based on this. All right. Fair enough. Let's see. Let's have one more question based on this. So the first part I'm keeping the same. I'm not going to change that. I'm going to change that. This part, let's say this time instead of 53, we'll have 60 degree. Okay. I'm just giving one more for you guys to understand it properly. So the first part remains same. The only change what we have is from 60 degree over here. That's all. Okay. So we're going to do it quickly this time. So let's say this time when it is released from 60 degree, let's have 60 degree. Okay. Now, okay, very quickly, this angle is 60 degree. Of course, this is going to be 60 degree. Let's say again the tangential acceleration. Now the forces will be mg downward. Here we'll have Fe. Okay, the same concept. Angle is going to be how much? 60. Even this is going to be 60. Even this is going to be 60. Okay, so force is going to be same. Now this is going to be your mg sine 60, and this is going to be your Fe cos 60, and the rest is just mathematics. We can do it. Well, so over here the acceleration should be, I'm going to write ma should be equals to how much? Mg sine 60 is nothing but root 3 over 2 minus Fe, the electrostatic force would be how much? Well, okay, I think I should write it a little down. So m times of a should be mg root 3 over 2 negative Fe k q square sine 60. This length should be how much? Root 3 by 2 times of L. Fair enough. So the entire length should be root 3L. So this should be root 3L whole square into cos 60 is how much? 1 by 2. I hope this is correct. If anyone have any doubt, do let me know. So yeah, kq square by 3, because this length should be how much? If it is L, this is going to be L sine 60, and L sine 60 is going to be root 3 over 2 times of L. Yeah, that's all is equals to ma. Now, so ma should be how much? Root 3 over 2 mg minus, I'm going to have kq square over 3 times 2, I'm writing directly, 6 L square. So kq square over L square is nothing but 2 mg. So I'm going to have ma equals root 3 over 2 mg negative 1 by 3 mg, right? So m going to be cancelled away. I'll be having a equals root 3 over 2 g minus 1 over 3 g and yes, so root 3 over 2 minus 1 over 3 g. That's going to be the acceleration in this case. I hope you guys have understood this one. So yeah, I mean, like we have covered up a couple of questions in the pendulum part. One question I've given as the homework. I'm going to discuss that now, which we had in the last video. Now in this Coulomb's law, we have seen the normal questions when we have to find the distance at which equilibrium is existing. We learned how to find the normal force, between two objects, between the three mass system, three charge system, when we had placed them at equilateral triangle, maybe in any sort of quadrilaterals, vortices and all blah blah things. And we have seen the pendulums, we have seen the questions based on the SHM, and this one again, it's a good question, guys. Learn this properly. You might see this in any competitive like JEE and NEET exams. They might come up with some values. I'm just doing it in the general form so that you guys going to learn the concept as well besides solving it. Okay, now let's move on to the next part of this. Okay, let me erase this. Guys, now we're going to see one more questions in this topic, where I'm going to introduce the vertical circular motion and of course the electrostatic all together. Okay, let's say example 4 over here now. So I'm sure you guys have done class 11th properly. Let's say if I have a charge over here of Q, let's say mass M, and another charge over here of, let's say, same Q and mass M, hanging with a certain string, let's say of length R. Okay, now I just need to provide some velocity to this charge, let's say U, so that it completes a vertical circular motion, right? Now I'm sure you guys have done class 11 properly, where you know that the minimum speed that we need to have a complete circle should be more than or equals to 5 gr, right? I hope you guys remember all this stuff. Okay, so what happens over here in this case, when I just give certain velocity to this mass over here, it starts going up, it reaches over here and then goes to the top. Okay, and at the top, if the velocity remains, I mean, like the tension in the string, or maybe the rope, whatever you say, if the tension at the particular top position is not slagging, if there is a tension existing over here, okay, then the body completes a vertical circular motion, right? There should not be any slag. If the moment slag comes over here, the body will fall down. So we have the maximum probability of the body to fall at this position. Let's say this is a position A, B and C. Of course, the tension keeps on decreasing, right? The moment it starts going up, the tension keeps on decreasing, and it's going to be the minimum at this particular position. Okay, now if it survives, it will make a complete vertical circular motion. So the tension in the string at this point of time should be T, again T, this should be existing. If it's not there, so the thing is, T at that point should be more than or equals to 0. Let's suppose this point is C. So tension at C should be more than or equals to 0 to have a complete vertical circular motion. If it becomes probably less than that, the body gonna fall down. Agree? Keeping those things in mind. So in this case, when we do not have charge, when we only had the mass, there was only tension, and the force was the gravitational pull, right? But in this case, we're gonna have an extra force, but that's gonna be electrostatic force acting on that. Okay. So my question to you: find minimum value of U to have a complete vertical circular motion, vertical circular motion. That's a question. And the charges are given as Q, and of course the masses are M. Okay, let's have a look at this one. Let's say let's say all the forces acting on this object. I'm gonna show you at 2 points. Let's say here, and of course we're gonna talk about this position. So if I look at this point, the forces acting on this should be your mg downward, definitely, They're going to be electrostatic force, that in this case it should be in this direction, isn't it? Because the charge is here. So the electrostatic force will always be in this direction, and there would be force tension over here, right? So that's how things gonna look like, and then of course it's components and all, right? Okay, let's see what's gonna happen now at this particular position. At this point, okay, I'm gonna just clean this up. Okay, I'm gonna write it here. U should be more than equals to 5 GR. Okay, that's for the extra bit of knowledge. There's going to be an electrostatic force acting upward. There should be tension in this direction, and of course mg over here, and here we're going to have electrostatic force, right? Now we know that tension should be more than or equals to 0 over here, right? Yeah. So let us see the value of tension. Tension over here should be how much? T should be equals to F, this is centripetal force, that is mv square over r, not Fe. It should be Fe plus mv square over r negative mg, and that should be more than or equals to 0 to have a vertical circular motion. Let us find the value of Fe, blah blah things. We can do that over here. Now what's the value of Fe? It's gonna be kq square, of course. So I'm gonna replace here itself to save some space. Kq square over r whole square. All okay, guys? Now I just want to get the value of u. Here we have v. So what I'm going to do now, I'm going to use the work energy concept, right? And that says that the total work done by all the forces, should be equals to change in kinetic energy, right? That's the work energy theorem. So we're going to find out the work done by all these forces acting over here. In this case, that's going to be a simple approach. Fair enough. Now what is the work done by electrostatic force? Okay, let's say talk about mg first, or maybe probably tension first. Okay, so let's say the work done probably by your tension. Here we have I can say that this part, so let's see how many forces are acting over here. So we have one force, that is tension. So let us find the work done by the tension. One more force is the gravitational pull downward. So we're going to find the work done by the gravity, and then of course the work done by electrostatic force. That should be the change in the kinetic energy. So the final kinetic energy at this point is, let's say, v over here. So the velocity at this point, assume that it's v. Okay, so half m v square, initially it was how much? U square, half mu square. That should be the relation. I hope this is clear to everyone, right? There shouldn't be any doubt about this. If you have any doubt, you can pause the video and rethink what we've done so far. And still you get some doubt, do write in the comment box. I'll be helping you out there. So the net force, the total force acting on this charge is tension by tension, your gravitational pull, and the electrostatic force. I think that's enough. We don't have any other force acting over here. Now let us see the work done by the tension when the body moved from here to here. So tension is this direction. Okay, so the work done by the tension should be how much? 0, right? Now by gravity, so the body has moved from this position to that position, right? And the gravitational pull is acting downward. Angle between the gravitational pull and the displacement is how much? 180 degree. So can I say that should be how much? Negative of mgh. In this is h is how much? 2r. So minus 2 mgr. Clear, all of you? That should be the work done by the gravitational pull. Okay, fair enough. Electrostatic. Okay, this is acting along the tangential, right? So there is no displacement along the direction of this, right? All the time it's going to be perpendicular to the displacement. It's happening in this way, displacement is happening in this way, and all the time force is acting at a right angle. So anyways, there's not going to be working over here, right? Now, so the work done by the electrostatic force should be how much? 0. That should be equals to half of mv square minus half of mu square. Alright guys, now from here can I get the value of v in terms of u, which I'm going to put it over there. I'm going to get the value of u. Agree or not? Okay, so what I'm going to get over here, I'm just going to write mv square over 2 should be equals to how much? mv square by 2 should be equals to half mu square minus 2 mgr. So mv square should be mu square minus 4 mgr. Alright, let me replace this over here and I'm going to get the value of minimum velocity u, right? So let me clear a part of it. So can I just erase this part of the board? I think you guys have already noted down this diagram, this figure. So let me just erase this. So from here what I'm going to get is kq square over r square negative mu square minus 4 mgr over this r negative mg should be more than or equals to 0. Okay, so if I just solve it, I'll be having mu square, okay, negative of 4 mgr, okay, and if I do the calculations, I'll be having, let's say, minus 5 mgr. Fair enough? Okay, well, this should be plus, okay, plus. Over here, over r should be more than or equals to minus kq square over r square. So mu square should be more than kq square over r plus 5 mgr. So u square should be more than 5 gr, okay, minus kq square over m. So u should be more than 5 gr minus kq square over m under root. So the minimum velocity should be how much? Kq square by, fair enough? I think everything is okay. Okay, yeah, okay, there is something, this r should be there. Alright, I just missed out this thing. Okay, so it should be 5 gr minus kq square by mr. Fair enough guys? So this is actually a good question. Probably they can ask you questions on this structure giving some value. So you should not be afraid of that. You can just go ahead and solve it. Please note it down and then we're going to move ahead. Alright then, now it's time to discuss the homework question. Okay, so I'm sure you guys have remembered the question that there was a case. So this was a homework question. So yeah, let's say there is a charge q over here and mass m, and of course it's a charge over here q. Okay, there was no charge over here. Let's say the charge q and mass m, it is actually fixed to the wall. That was a question, you know, and we had a charge over here of mass q and q charge and mass m, and we were supposed, and this is existing in the equilibrium at, let's say, suppose angle theta, and I just asked you to find the tension in the string when this system is at equilibrium, right? There was a question. Okay, we can go ahead and solve it by the normal method. It will take a lot of time. Guys, I just want to tell you something about the Lami's theorem before I just solve this question. There's something called Lami's theorem. I'm sure you guys have heard about it. If not, I'm going to tell it right now. So it says that, okay, if three forces active on a body in such a way that the body is in equilibrium, then the ratio of the force over the angle opposite to that force to all the forces is a constant. So what it says that, let me just explain this. Let's suppose if I have a force F1 in this direction, F2 in this direction, and let's say F3 in this direction, let's say making it angle alpha, let's say beta, let's say gamma, and if it's in equilibrium, that is the net force at this particular point is 0, then according to Lami's theorem, F1 over sine of alpha should be equals to F2 by sine of beta should be equals to F3 by sine of gamma, and that should be equals to some constant k. That is Lami's theorem. The thing is, the forces acting at this point should be in equilibrium, that is net force should be 0 at this particular point. Okay, let us try and figure out, can we apply this theorem over here or not. Okay, now over here the first force should be mg acting downward. Second, of course, is your tension in this string in this direction. Okay, let me make it properly. Now, you know, the electrostatic force should be, if let me make a dotted line over here, it should be somewhere in this direction, Fe. Now the main important part of this question is to find the angle between them, right? Okay, let's say this is theta, let's say this is probably phi. Even this is going to be how much? Phi, because these two are, let's say length is equals to L and L equal. So this angle is going to be phi. Well, it means this should be how much? 180 minus phi. So against mg I got the value of the angle. Since I'm looking to find the tension, I must be careful about this angle. Agree all of you? Okay, let us try and find it out, this angle. Well guys, I'm like, there's different ways of finding it. I can see that these two going to be parallel to each other, because this is always going to be vertically downward. So can I say, let me use other marker, if it is phi, even this is going to be phi, alternate angle. Agree? So if it is phi, this angle should be how much? 180 minus phi. I think we are done with this, right? We got the things which is essential to solve this question. So can I just write tension over 180 minus phi equals mg over 180 minus phi. I hope you guys agree. Cancelled. So it's going to give me tension is equals to mg. So that's the beauty of Lami's theorem. If I know this theorem properly, I can solve these kind of questions quite easily. All okay? Now, one more thing, I just want to probably discuss a couple of questions based on the vectors laws, a vector form of the Coulombs. Well, that will take probably 20 minutes, so I don't want to continue in this video. What I'm going to do, I'm going to put up a next video in which I'll be precisely discussing on the vector form of the Coulomb's law. Well, the vector form is used when we have directions coming up in the picture. So the vector form gives you magnitude as well as direction at the very same time. So that is important, and normally when we have questions based on the three dimensions, when we have probably the charges placed in 3 dimensions, that vector forms of the Coulomb's force, Coulomb's law works really good. So guys, I'm going to do that in the next video. Okay, so for now, just keep practicing and make sure that I think by this time I have done all the questions based on the Coulomb's law. If anything is missing, if you guys just want to ask me some questions, please send me in the comment box. I would be happy to help you on that. All right, keep studying and thanks for watching. See you guys very soon. Bye bye.